Engineering 305. This is Chapter 5, Problem 5. There's an 8-foot long steel. Now, remember the last problem we had steel and it was a Young's modulus of 29,000. Now we have steel at 30,000. That may contradict something that I'll tell you in class one of these days, but that's, you got to be in class to get that knowledge. The bar has a 1.5-inch diameter over half its length. See how that looks bigger bigger on this side? Yeah. Inch and a half on that side, 1 inch on the other side, but it's half and half. That helps us out with part 2. For the axial loads shown, determine the change in length of the bar, and then so we're going to find delta total, and then find the change in length of a bar if it has a uniform cross section that would be the same weight as the bar in part A. In other words, what they're really saying is, look, now instead of going inch and a half and inch, oh wait, we got to do the same weight. It's going to be a harder problem than I thought. I thought I'd just be able to jump to 1 1/4 inches, but that's actually not quite right because area doesn't scale that way. So, but it's got to have, this new bar has to have the same volume. That's what we're looking for. So, or it has to have the average of the two areas, another way to look at it, since they're both 4 feet. And we'll do that. That's part B. Let's just start with part A right now. The change in length of the bar for the load shown. Now, similar to what we've done, or what I hope you've seen, is that the total deflection is equal to the deflection of the big bar plus the deflection of the small bar. And that deflection is equal to P, and I'm just going to say B because that's big, length of the big, area of the big, Young's modulus for the big, plus, now we got to put in the change it for the small, which is the load in the small, the length of the small, the area of the small, and the Young's modulus for the small. Now, Young's modulus for the big and the small, those are the same. So I could simplify this, but for right now, yeah, that's fine. All right. What is the load? What is the load in the big section? Excuse me 1 sec. Sorry, there we go. What's the load in the big section? It's 10 KSI. And what is it, in compression or is it tension? It's in tension. It's in tension. So equals, don't want that color. This is 10 kip. Did I say KSI? I think I did. The length of that bar is 48 inches. The area, now that is a 1.5-inch diameter solid. Pi 1.5 inches squared over 4. And Young's modulus, yeah, I'm going to put it in. I'll put it in 30 E6. I was going to decide whether I wanted to consolidate terms, but we don't want to do that. Plus, what's the load when I look at that section through the second half, through the smaller half? Well, it's now 20. It's now 20 kip. Okay. 20 kip times, it's also 48 inches long. It is now pi times 1 squared over 4 inches. It's in inches. That's in PSI. And then this is 30 E6 PSI. Do the units work out? Well, I've got my per square inch, and I got square inches here, so this is just in pounds. And pounds cancels with pounds, so I'm left with delta. So yeah, that all works out. Equals, well, this first term is equal to 9.06 E-3 inches plus 40.76 E-3 inches. 4 times more. 4 times more. Why is that? Well, look at the terms, because everything's relationship, so we should get this. This is, I've got twice the force going on here, so that should double it. And then this term, this is going to be, when I square 1.5, I get 2.25. So I've divided that. That's made that stronger and stiffer, also by about a factor of 2. So that all makes sense. Maybe I shouldn't have boxed it, because what I really want to box is delta total is equal to 0.0498 inches. All right, there, that's part A. That's part A. Now we got to redo it. Easier and harder. The first thing we have to do, go back, it's got the same weight. So what would be my average area? Average area. Well, if I go back to some of the back number calculations that I did above, and I have to redo it. The area of the big is equal to pi times 1.5 squared divided by 4 inches squared. Area of the small is equal to pi 1 over 4. Oh, the 1 is squared. Like, that makes a difference. Inches squared. So let's do that calculation. Equals, so there we go. So I did the calculation. I got the area of the big is 1.76 inches squared. Area of the small is 0.785 inches squared. So the average area is 1.275. So if I'm going to keep the weight the same, that's going to be my area for the whole thing. Now the beauty is, well, I thought the beauty was, I still have to calculate delta total. Why? Because even though the equation is PL over AE plus PL over AE, and now I have my E's the same, and I have my areas the same, and I have my L's the same, don't I? Yeah, they're both 4 feet. Yeah. But my P's are different. So I've got 10 plus 20 L over AE. And that's okay. I can calculate that. When I do that, I get delta total is equal to 0.0376 inches. Now, many of you would say, that's the end of the problem. Wait, I draw a box on it. Now I'm all good. Done. Woohoo! No. Think about your answer. Think about your answer. Shrink it, dink it. Here's my deflection here. Here's my deflection here. And it has the same weight. It has the same weight. So if deflection is important, the uniform bar works better in this situation. In fact, I would probably argue that maybe we should have taken the bar and reversed it so that we had twice as much area where we had twice as much load. And if we redid that calculation, I bet we'd find that we get less deflection yet. Maybe I should do that. Maybe that would bore you. You know what? I'll hit the pause. I'll do that, and then I'll prove my point. Because I've got the pause button, and you don't have to be bored. Kind of a bummer there for me. I equalized the deflection. You can see I ran the calculation up here. I just took this equation and kind of copied it over, but reversed the loads. And then I got new numbers, and I got 0.0385, a little bit larger, actually. A little bit larger. So this does a good job by balancing that. I would have thought I could do better, and I probably can do better, but by just flipping it, it isn't better. So, well, there you go. You learn. So, but we have to think about how we distribute our loads, how we distribute our materials. And anyway, I hope you're doing well. And don't worry, there's more to come.